Okay, this section is thinking about derivatives as rates of change. And so there's a lot of application type problems in this section, and I'm just going to kind of go through some of the application problems and talk through how we should be thinking about derivatives in certain situations. So we're going to talk about, like, if I have a position function, the rate of change of position is how much it moves over a rate of time. So in some certain amount of time, the position changes, it's moved, it's sped up or slowed down or accelerated, that type of stuff. Well, its velocity is it's immediately the rate of change of position to time. If I take the second derivative, I get acceleration. If I take the third derivative, I get jerk. If I take the fourth derivative, it's this thing called jounce or snap. And then the joke is, after snap comes crackle and pop. So the fifth and sixth derivative are kind of joked about as crackle and pop. But there's not really any names for those, and then the higher ones certainly don't have names. But you can take rates of change and say something about a function. So let's do just a position function one real quick. Let's say that s, the displacement function, is usually written as s, and it's a function of time usually. Let's take a sort of standard example. Let's say I've got 100 minus, say, plus 25t minus 16t squared. A lot of times in your position functions, you're going to either see like a 16 here or a 9.8 over 2, or like a 4.9 there, a negative 4.9 there. And that comes from the gravitational constant. Bodies fall at 32 feet per second squared, so this is where we get my acceleration. 32 divided by 2 is 16. And 9.8 meters per second squared, and 9.8 meters in half is 4.9. So you'll often see a minus 16 on the t squared or a minus 4.9 as the coefficient on the t squared. So this one, we'll be thinking about it in feet and a falling body. The body is going to start at 100 feet. I'm going to throw it upwards at 25 feet per second, and gravity is going to pull it down at 32 feet per second squared. That's kind of how this situation works. So let's see why that's true. Well, the derivative, the rate of change in position with respect to time, so ds dt. If I take the first derivative, I get 25 minus 32t. So the initial velocity is 25, and the acceleration is negative 32 per second. So if I was going to have things as velocity, if I labeled all these units, this unit would be feet per second. This would be feet per second because it's not multiplied by anything, it's just a constant, so it has to have the same units as what's on the opposite side. Here I've got a units of seconds, and so to get to feet per second, this is feet per second, this is something times seconds, this must be feet per second squared. So that all of the units match up, I can take feet per second away from feet per second, and then the subtraction works fine to get feet per second on the other side. Okay, so the next thing that I could do is I could take the second derivative, d squared s dt squared, right? And that's going to give me minus 32. And here, this is still in feet. The change in time, though, is in seconds squared. So this is feet per second squared, and this is feet per second squared. So I've got acceleration of negative 32 feet per second squared. My velocity, my initial velocity was 25. It decreases after so many seconds. My initial position, if I put in time equals 0, I get 100. So the picture looks like I'm starting up here on the x-axis at 100. I've got an initial upwards velocity of 25 feet per second, but acceleration down, so it's slowing down. It's not going to get all the way up to 125, but it'll get up a little bit above 100 because I threw it upwards, and then it's going to accelerate down like this until it hits the ground probably. But this function, if I can graph it everywhere, looks like an upside down parabola. Okay. If I wanted to figure out where it hits the maximum, I would be looking at where the velocity is equal to 0, right? And this is my velocity, so I would be wanting to solve 25 minus 32t equals 0. And that would tell me where things hit a maximum. That's where the derivative is 0, right? It is no longer increasing in y. It's not also not decreasing yet in y. It's where it changes from a positive slope to a negative slope. And to do that, because the slope is continuously changing, it has to change at the point 0, right? That's the intermediate value theorem. To go from something positive to something negative, you have to go through 0 if you're continuous. So we would solve this equation for t, and that's going to give me 25 over 32 equals t. That's the number of seconds until I reach my maximum. So this is going to be 25 over 32, right? And whatever I get when I plug in 25 over 32 into the function would be the y output, right? So this would be s of 25 over 32. So 25 over 32. Okay, so that's one sort of example that we'll see with these types of situations where we're looking at rates of change. That's kind of a common one with the physics stuff going on. Another one we might see is maybe you've got a business or a econ problem. Let's say we have a profit function. And this profit function is going to relate the number of things that you sell to the amount of profit that you make. And so let's say our profit is a function of Q. Profit's a function of quantity. And let's have a 300 times Q. Maybe you sell your things at $300 a piece, but then it costs you something, right? Maybe it costs you some amount of dollars per Q, per quantity. That's already taken into consideration here. But then you get better at this as you do it. So instead of taking away all of that, maybe I get 15Q squared back, and I also have to take away 2Q cubed, though, because I get better at it, but the more that I do, the sort of return I get on doing more lessens and lessens. You get more maintenance if you try and throw stuff through faster and faster. So for our situation, this is going to be our profit function. You get more return as you do more, but it also costs you more in maintenance as you do more. So you've got this kind of trade-off stuff going on. Okay, what we want to know is, say this business wants to make it look pretty good. They're still growing, and they haven't quite maximized their profit yet, and they know that they have to, if this is their profit function, they have to hit this goal at some point in time. But this year, what they want to do is they want to aim so that it looks really good on next year's books, that they are growing the fastest they possibly can grow. So I want to know, what quantity should they produce this year So what quantity do they want to produce right now so that in the future it shows that they are growing the fastest they possibly can? They know what this profit function is, but they want their books to show that they're growing really fast next year. So they are at a position of maximum profit growth. So up here, we showed that to find the maximum of the actual output quantity, I would set the first derivative equal to 0, right? But I want the maximum growth. So the growth rate would be the first derivative. To find the maximum growth rate, I would want to take the maximum of where the first derivative is. So I need to set the second derivative equal to 0. Okay? And this is going to be called a point of inflection. And I'll show you why it's a point of inflection. But so I've got P prime at Q is equal to 300 plus 30 Q minus 6 Q squared, and P double prime, that's going to be 30 minus 12Q. Okay, so P double prime at Q is equal to 2.5. Is equal to 0 when Q equals 2.5. Okay, and that's the point that we want to aim for. Why is that? Well, like I said earlier, on this graph, I've got this cubic, and if I plug in 0, I get 0. It's an upside down cubic, so for a while I don't get any growth. But at some point I'm going to outspend on or outproduce things, so I won't be able to make a profit anymore because I won't be able to sell anything, right? So it's going to sort of turn around again and go this way. Okay, so I have to build enough to make a profit, and then after I make a profit, if I produce too many things, there won't be enough demand for them, and I will have overproduced the demand, and then my profit goes down again. Okay, so I've got this sort of shaped curve, and in here somewhere I've got a maximum rate of growth, right? It's growing faster and faster and faster. This is the steepest that the curve gets at some point, because at this point it turns over and starts growing slower and slower until it hits 0 again, right? It starts at 0, it starts growing, turns over, stops growing. This is my maximum profit. This is my maximum, well, not maximum loss, because I could overproduce and have a bigger maximum loss. But in the feasible range of where you're going to produce stuff, this would be your maximum loss. You'd want to avoid that for sure. I want to position this company right here at this point in time of maximal growth so that the books look really good next year and people buy into my company. Okay, so I find that, and that's the point of inflection. That's the point where it stops going curved up, right? This is sort of opened up, and then it goes to curved down, right? So I've got curved up on the left and curved down on the right. This is the point of inflection. Point of inflection. And in business terms, this is sometimes called the point of diminishing returns. I'm not quite sure how to spell that, but it's diminishing returns. Okay, and that's because over here, when you put dollars in, you get more dollars out, right? Over here, you put in the same amount of dollars, like this dollar here gives you good stuff, like lots of stuff. This dollar here doesn't give you as much stuff anymore. This dollar here gives you stuff, this dollar here gives you more stuff, more stuff, more stuff. Now this dollar gives me less stuff than I had for the last dollar that I put in. This one, less yet for the last dollar I put in. Less yet, less yet, less yet. So as I get to this point, this is the point of diminishing returns. But that has to do with the second derivative and growth. Okay, so what we're going to be looking at is how do these rates of change sort of correspond to real life situations. And you're going to be looking at sort of concavity of the graph. Is it curved up? Is it curved down? How fast is the slope? changing. What is the slope? Is the slope 0? Is the slope positive? Is the slope negative? And you're going to try and put all of those things together into understanding these word problems that are coming from this section. And that's takes some effort, and it takes some thought, and it takes some knowledge of how these things should be thought of. And so we're going to get some practice on that this section. Okay. I'll see you guys on Monday to talk about that stuff.